everyone. Good afternoon. I hope you enjoy your lunch. I'm Sadegh Solati. I have been with SoundCloud since 2021. Today I'm going to tell you how we have protected SoundCloud from certain types of DDoS attacks. But before I begin, I like to show my respect to people of Iran who are fighting on the streets for a... Thank you. For a better future in a revolution led by women with the motto of woman, life, freedom. And since the beginning of this revolution around 2 months ago, more than 300 women, men, and children have lost their lives. Their bravery and sacrifice has lit up the way out of a dark dictatorship for our nation. But back to our business. SoundCloud, like any other famous platform on the internet, is the target of DDoS attacks. And these attacks are done by different sources with different motives. Some of them are done by the people who are not happy about a track that is published on our platform. Some of them were done by people who are trying to abuse our monetization system, meaning they're trying to create false likes, plays, or comments on a track. Some of them are done by some citizens of the internet who picked a bad hobby for themselves, and they just do it for fun. And there are another group that we call them weapon tests. They're done for educational purposes. Someone has created a new DDoS tool, and they want to test it. Where should we test it? We test it on SoundCloud. And to all of these types of attacks, we should add different duration and different frequency. These attacks can last from a minute to a few hours, and they can happen from not at all to 20 times per day. When under these attacks, one of the solutions that we have is to go to our CDN provider and ask them to enable their protection or their DDoS protection on our service. Although it's a very valid solution, but the question is it the best solution for all of those attacks, for all of those occasions? Let's see. The first and most significant problem with DDoS protection services is they are expensive. And because they are expensive, we cannot keep them on for an extended period of time without breaking the bank. Besides, when we want to enable these services, most of them, they take from 2 to 15 minutes until they are in action. And as I said, some of these attacks that we are trying to fight, they last less than 2 minutes. And by then the protection is activated, there is nothing to protect us from. And okay, before I tell you how we protect SoundCloud from these types of attacks, I like to tell you a bit about our infrastructure. If you have been to Berlin, oh, sorry, it's got a bit messed up. So what we needed? What we needed was a first layer of defense on our edge infrastructure that is decentralized, so we don't need to care about the high availability. It has to be easy to engage, meaning it shouldn't last 2 to 15 minutes to enable it. And most importantly, it has to be cost effective. Because these attacks we are fighting, they have different frequency and different duration, we wanted this system to be engaged all the time. So whenever they happen, we are ready to fight back. But before I tell you the solution, I need to tell you about our infrastructure a bit. In case you have been to Berlin, you probably have met this handsome guy with a hat on our pedestrian lights. His name is Ampelmann, and we have borrowed his name for our edge infrastructure. Ampelmann is consisted of 3 components and many automations around it: CDN, DNS, and Terminator. CDN and DNS, they are self-explanatory. We don't want to spend our time on them. What we want to discuss today are terminators. Terminators are the first point in our infrastructure that we receive our requests from. And we have several regions in the world that we deploy terminators in, and in each of these regions, we have 4 different pools. And based on the size of this region, this pool can contain from 6 to 15 instances. And the software that was running on these instances used to be HAProxy community. In HAProxy community, we have a very fast in-memory storage named a stick table aggregator. Using a stick table aggregator, we can store information from a request, and later on, we use this stored information and decide about the destiny of that request or any further requests. Here you see an example of how we can configure such a thing. At the first line, there's a backend. We define our table in there. In this table, we store IP, and the value will be the rate of HTTP request in last 1 minute. And we use this backend in the front-end section afterward. What this configuration is doing, it is tracking all the IP addresses who try to log in into our platform, but they have failed to authenticate. And on the last line, we check if the number of failed login attempts has been more than 10, we don't allow any further try. This is a very good tool. It can be helpful for us to rate limit the requests that we are receiving, therefore protecting ourselves from DOS or DDoS attacks. But it has an issue, and that issue is all of this information are local. Means that the informations are not shared between instances. And as I said, our system is distributed across several regions, and each of those regions have several pools, and each pool has several instances. And when a request enters a region, we don't have any control over where it's going to land, and we don't want to, because the whole thing has to be stateless. So we needed a system to share the state, share this tracking information in stick tables among all of those HAProxy instances so we can make a better decision. By upgrading to HAProxy Enterprise, we have got access to a tool named a stick table aggregator. A stick table aggregator, as the name suggests, receives all of this information, all of these stick table information from HAProxy instances, and aggregates them together and feeds it back to all the instances that are connected to it. What we liked about this solution was it was an extension to our existing infrastructure, meaning we didn't need to change much and we didn't need to invest on new hardware. And because it's an extension to our existing system, and our system is already designed to be decentralized, this system automatically is also decentralized. And we are not going to invest on new hardware that makes it cost-effective. And also, because it's a part of HAProxy, it means we are very flexible, and this flexibility comes very handy later on. So there are several ways to set up a stick table aggregator. You can set it up in single layer, multi-layer, or HA. What we decided to do at our first attempt was the multi-layer. And the way we configured it, every region that I talked about got one top-level aggregator, and every pool in that region got one middle-level aggregator, and the instances in each pool got connected to their own pool aggregator. And the flow of information is HAProxy instances collect these metrics from the requests. They push it up to the aggregators. Aggregators do some aggregation and pass it up to the top layer, to the region layer. And the region one will collect all of the information from every pool, aggregate them again, and feed it back to the mid-level, and the mid-level, again, goes back to the instances. And we set up this system in a monitoring mode. So we didn't want to block anything yet. We just wanted to see if it is capable of detecting anything. Our initial results were not promising. What we observed that there was only one CPU core utilized on these stick table aggregators. And this utilized CPU core was all the time utilized to 100%. At the same time, we could see that we could see some malicious activity on our other dashboards, but this system was not detecting anything. Most probably because of this CPU bottleneck, it was lagging behind, and by then that the aggregation was done, and we have decided, oh, we have reached a certain threshold that now we can block this request. The requests were gone because the system was slow. And also, what we expected was the top layer to have less utilization than the middle layer, but all of them were equally utilized. And because this system was under lots of pressure, this stick table aggregator process used to die and crash very often. We have reached to HAProxy and asked them for their help. They told us that the stick table aggregator is using peer protocol, and peer protocol is not a multi-thread friendly protocol. And one of the fast solution they could provide for us was use a faster CPU. It is a valid solution, it helps, but how much faster CPU could we get? And besides, that's not a sustainable way of scaling this system. At SoundCloud, we like to scale horizontally rather than vertically. We really like this solution, and we didn't want to give it up that easily. We decided to give it another try and went back to our design paper again. In our second attempt, we decided that, okay, we have 2 layers of bottlenecks. Let's put aside one of them and keep it away until we are 100% sure that we need this second layer. So now in the new design, every region got only one stick table aggregator. And all the instances in that region were reporting to that one aggregator. Now there was a time to ask the question, the right question. Is there a way to run multiple instances of a stick table aggregator and forward only a part of request to each of these aggregators? So we balanced the load. We needed a solution without any modification in the existing tools, because that was going to be time consuming and we didn't want to get involved with it. Running many instances of a process listening on a TCP port is quite straightforward. We created 40 instances of a stick table aggregator listening on one machine from port, here in this example, from 20,000 to 20,039. We went to our templating language, created a for loop, and created 40 peers in the HAProxy configuration. In case you haven't seen the peer configuration before, the most important part of this configuration is the last 2 lines of each section. And the only difference that these 2 lines have from each other is one of them has the suffix .local and the other one has the suffix .zone. When HAProxy is collecting the metric, it will store the information in the .local table. And then this information will be forwarded to the aggregator. Aggregator will aggregate this information and feed it back to the .zone table. And when HAProxy wants to make a decision about the request, when they want to make a cluster-wide decision, it always evaluates the IP, whatever record, against the .zone table and not the .local one. So far, we have answered the first part of the question. And it was easy, just running 40 instances of a stick table aggregator. But what we need now, how do we balance the requests to each of these stick table aggregators in a way that every IP address will only land on one of these nodes, and it will always land there. Because if it goes to another instance, then we are counting the IP addresses, the number of requests that every IP address is making, twice in 2 different locations, and we don't have a total sum, and we cannot make a correct decision based on this information. As I said before, because we are using a HAProxy, it means we are flexible. In this piece of configuration, you can see how we solve this problem. As you can see in the first line, we have defined a variable in the request. We are getting the IP address of the user from HTTP header set by someone else, and we calculate a checksum on this IP address. And then the output of this checksum will be a number. We divide this number by 40. This is the number of instances that we have. And whatever the remainder of this division is, will decide on which stick table aggregator this request is going to land on. And this calculation will always be the same on every instance. That means that every IP address, doesn't matter on which node we have received it, it will always be accounted on one stick table aggregator. And when the accounting is done, when the aggregation is done, later on you can see that we have this ACL rate limit, and that is looking up the IP address in all of those tables. If the number of requests have been more than 100 in this example, this access list will be true, and later on we will block this request from going further. And this is now under, this sharding, as we call it, is now under implementation by a HAProxy team, and soon you will have it out of the box, and you don't need this repetition anymore, like having 40 peer definition and then 40 times evaluating one ACL. But let's see how good this system works. This is the dashboard of one of the services that we are protecting with this system. As you can see here, every vertical line is showing 10 minutes. And the green line is the number of 200s. The blue line is the number of requests that we have blocked. They were malicious requests. And the errors are also measured on the right axis, which has a smaller number because we care about the errors. We want to see the little amount of error as soon as possible. As you can see in this picture, there are 3 waves of attacks. The first one begins. This service is receiving around 98,000 requests per second. The attacks begin. There will be some errors because most of these requests that we get in these attacks, they are invalid requests. Our application cannot process it. And they have passed because in these attacks, for example, there will be 4,000 IP addresses used. And until our system detects it, there will be some leakage requests that pass through. And the errors you see here are because of those leakage that happened. But the important point is, on the first attack, first of all, this system is very fast. You can see this line goes up almost vertically. That shows the system is very fast, and the system is serving 98,000 requests. The attack is 200,000, and there is no effect on the service at all, and the service was completely protected. We go forward, there's another wave, and that one lasts for 10 minutes, and the third one that peaks at 225 RPS. And this is very helpful for us because if it wasn't because of this system, we should have always be ready to upscale this system. And upscaling always takes time, and it reduces the quality of the service we are offering to our customers. And this saved us a lot. And the current hardware in use that now we are using for this system, it is running on a machine with 40 CPU cores. And the maximum load that I have seen on this machine is around 20, when under very big attacks that sometimes gets to 300,000 RPS. Another bottleneck that we have faced in this system is the network. This system needs lots of network transfer between HAProxy instances and aggregators, and again, back to them. So if you want to use this system, make sure you have 10 gigabit per second. And another point to compare, like I said, that we have load 20. The first version of this system was using one CPU core, and that one core was always 100% utilized, which means load 1. So we needed a system 20 times more stronger. But this system is not perfect. Still, from time to time, very rarely, the HAProxy instances, they lose their connection to the aggregators. After, most of the time, 98% of the time, they will recover after a few minutes, but sometimes they don't. But because we are deploying our HAProxy instances very regularly, after each restart, the connection will be established again, and everything will work. Because we are now using this single layer setup, we have a single point of failure, which is the aggregator itself. And because of the peer protocol limitations, we cannot have the HA setup using that sharding that we are doing. We decided to keep it as it is and just monitor it. Because if something happens to aggregator, we can just spin up a new machine, 5 to 10 minutes, it's provisioned again, and it starts working. And the way we monitor it, HAProxy Prometheus module exports one very nice metric, connected peers, and we just have an alert. If the connected peers is less than 40 for last 10, 15 minutes, someone will get alerted, and the on-call person will take care of the stick table aggregator, whatever problem it has. As I said, we wanted this system to be easy to engage and disengage. One of the other modules that HAProxy Enterprise provided us with is LB update. Using LB update, you can update an access list using an HTTP endpoint. The way it works, HAProxy will fetch an HTTP endpoint regularly, in this case every 60 seconds, and based on the content of that file that was fetched, it will update the ACL. Here in the first ACL, rate limit CIDR.lst, we use this feature as an off and on switch. When in this ACL, there is all the IP addresses on the internet 40/0, it means the system is activated. If we want to disable it, we edit this HTTP endpoint, and maximum 60 seconds later, this system engaged or disengaged. In another ACL, we use it for allow listing RFC 1918 IP addresses, and also sometimes some of our partners. And what we like about this module that we can easily give it to support team and non-technical people, and they can easily add IP addresses or remove it, manage it themselves, and that removes lots of load from our shoulders. Yeah, that was it. Thank you so much for your attention. If you have any question, I'm here to answer.
Sadegh, wonderful job.
Thank you.
So we do have some time for Q&A, just as we've done in the previous talks. Just please raise your hand, and one of our runners will come around to you. And it looks like we already have one question here.
Thanks for your presentation. I have 2 comments to make regarding the SPOF. In fact, it's very simple to replicate the aggregators, because you just have to configure 2 peers in your peer section, and you send them to 2 different aggregators. The same aggregation work will be performed upwards and downwards. You will just get twice the traffic downwards, obviously. But based on your numbers, I think it will pass even on a 10 gig links.
Yeah, so like instead of having the HA on the aggregator layer itself, we just send it to two aggregators.
Exactly.
And, yeah, it works. Yeah,
and
thank you.
The second point was, sorry, I forgot. No, it will come back later. Sorry.
OK. We are here.
OK, we do have a few that have come in online. People want to know more about Ampelmann. So you chose Ampelmann as the name of your solution. What inspired this? What inspired you to do that?
Well, to be honest, like there is no sophisticated story behind it. I think like someday someone was coming to work and they were standing on the light, waiting for it to be green, and they were at the same time thinking about, okay, what name should I pick for my system? Oh, there's Ampelmann. I call it Ampelmann. Yeah, but just wanted to have some reference to Berlin and where this is originated, and also that's the light, so it makes sure everybody passes safely.
Sure.
That's what the system is doing.
I like that.
It's me again. I remember the second point. We, in fact, already merged the mechanism for the sharding into 2.7, something like Dev 8, I think, something like this. So it was merged recently. However, it would be nice if we continue to discuss together, because for certain simple stuff like how to name the options, we were not aware at the development team of your exact needs. And we considered various names, and we thought that shards was okay because it corresponded to the stuff. Mm-hmm. But apparently, that's exactly the same term you plan to use as well. So it was fortunate that it was the same. But it's useful sometimes to be able to exchange closer on such stuff, so that we can make sure that what we can propose matches exactly what you need.
Thank you so much.
So we do have a few more online. Looking back at your project, what factors stand out as strengths or weaknesses of the new solution? For example, cost savings, reaction time, or overall complexity?
Well, one of the known weaknesses that now we have is we haven't integrated the GeoIP with this system. And when fighting DDoS attacks, sometimes it makes it much easier to detect if you know where are the origins of these requests and where are they coming from. Usually, the attacks that we get are from 2,000 to 6,000 IP addresses. And by limiting based on the country, sometimes we have less traffic in a country, and most of the attacks are coming from there. That makes it much easier to detect and block that country for a while until the attack has passed.
All right, we do have one more online. It's about the stick table aggregator. So how has implementing HAProxy's stick table aggregator improved your workflows?
Well, before having this system, we had to use these expensive services that our CDN provider was offering. And the problem with this system was, because we need to turn it off and on, so that was a operation overhead. And besides it, the services like ours that have high cache hit ratio, when you activate this protection, you are paying for the inspection of the traffic that is going to hit the CDN infrastructure, but what you actually care to protect is your origins, and you don't want to pay for that big amount of traffic that is not going to touch your infrastructure. But the CDN needs to do it because they want to know what to block and what not to block. That's like, not only it's expensive, but also it's not really cost effective. And you are paying for the inspection of 98% of the traffic that is not going to hit your region. So this was one of the motives behind doing this, and it costs lots of money. It saves a lots of money, sorry.
So what kind of DDoS attacks do you protect against using the system? Is it only HTTP level, or is it also other kinds of attacks?
This is mostly HTTP attacks, and there is a threshold. There is a point that, like on the network layer, we are quite protected because we have direct communication with our CDN provider, and that's a private link. But when it comes to HTTP layers, because we want to keep this nice encryption everywhere, after some point, we reach to a threshold that the blocking capacity is not a problem anymore, but that's the encryption capacity that becomes a problem. But most of them are HTTP, and the HTTP are the most challenging one to fight back.
We have one more online. Is the blocking of DDoS attacks happening in the data center or on the edge?
Well, our edge is the CDN. And if the attack is lasting for 6 hours, let's say, then we have to do it on the CDN level, because the attack that lasts for 6 hours is also going to bigger scale. We don't have the capacity to fight back with that attack. But if there are small attacks that happen regularly during a day, it happens that they went on for 20 times, but each time for 2-3 minutes. And the purpose of these attacks are just to make interruption. And now we can easily fight with these kind of attacks, and we just use the CDN, the edge, the actual edge, just for big attacks.
Great. Yeah. OK, so I think that's all the time we have for Q&A. Again, a huge round of applause for Sadegh. Thank you.
Thank you so much.